Laura. Thanks so much for joining me on this episode of Concentrating on Chromatography. I appreciate it.
Hi, David. Thank you so much for the invitation.
Abs-
So, I'm an analytical chemist. I collaborate with the Narayan group here at Michigan, and they do what I call really cool, crazy bioengineering. So, in general, biocatalysis leverages the chemical prowess of enzymes, nature's catalysts, which are really just better than us. They can do all their reactions in aqueous media. They don't produce any environmentally toxic chemicals. They're so enantioselective and stereospecific and just big jerks that make all us hardworking chemists feel a little silly. So, where direct evolution comes into play with this, and here I like to introduce Frances Arnold. She won the Nobel back in 2018, I believe. I saw her speak at PitCon, actually. Uh, Brilliant and hilarious. So, the theme behind directed evolution of enzymes for biocatalysis is that you identify an enzyme in chemistry, typically, obviously, within a microorganism, plant. And if you have any interest in the kind of substrates that's or scaffold of substrates that this enzyme works with, or just the general chemistry reactivity that it does, you can basically isolate the enzyme, sequence it. Now, this is where we get all crazy. We can mutate the sequence, re express it, and now you have mutants of the enzyme. And say you do thousands of mutants, you screen them against a novel substrate, or you screen them with the same natural substrate for perhaps a different chemical output. You can basically select whichever mutants perform best, whatever it is you're wanting them to do. And then you take your winner mutant and you start the process all over again. So you can do that 5 to 10 times. And the wider a net you cast with how many variants you're screening and how well you're navigating the space, the chemical space, you can basically have a really good mutant enzyme that can do novel, non native chemistry with the same properties that I highlighted in enzymes at the beginning of the answer. Just better than us.
And one thing that was interesting was that you mentioned presenting this work early on at ASMS and then again later on once more work had been done, and he joked about the stage the work was in when you originally presented it. But what did that original workflow or data actually look like, and what was the turning point that really allowed the work to evolve into the screening platform that you just published recently?
So I did pull up the poster from 2023 ASMS before before jumping on the podcast. And as I had told you before, it is comically bad. So, in terms of what it looked like, no real isomers. It was just these standards that another student in my collaborator's lab had said, oh, these are standards that will probably have isomers if things go well. So it was just check if they ionize well, check if they're contained well, and then at some point we'd progress over to actual isomers. So that was like on the sample side, no real isomers. And then, oh my goodness, on the droplet side, very, very slow. We're like 6 seconds per droplet and very ugly droplets. By ugly, I mean that typically, if you're doing droplets that are replicates, they look like, little rectangles, like just on off signals. They should all be the same height. They should have square flat top peaks. As my advisor says, he's always like, I want square flat top peaks. So these were just jagged, like the spacing, bad, 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 bad. But I was so proud because it took me a semester to just see a droplet. Because whenever you're trying to validate like a new ionization interface with droplets, and we'll get to this later, but it's just the whole thing. So, how do we get from that situation to this lovely paper, and then I printed it in gloss because, things just look nicer in gloss. So how do we get from that poster to this paper? Honestly, just being really intentional. Because it wasn't just about, oh, just show we can do this. It was like, no, I was like dead set on, I want to make a screening platform that actually works. And it was this like philosophical exercise of what does it need to do? How can I design it as modules, and how can I take these modules and just evaluate them for robustness? Because the running joke when I got assigned this project is, wow, droplets are so not robust and ion mobility is so obscure. Good luck. So I definitely think it was that mindset switch of, okay, how do I, as I said, it's like, how do I take the droplets and make them good in terms of sample introduction? And that was its whole science. And it was like, okay, once I have good sample introductions, which analytes are we working with, and like how do we make a method for that? So that was a second module. And then quantification, that was another module. And then it was like, okay, let's start to ensemble something real here, which is let's add the matrix, which was its whole thing. Let's add the matrix into this. And now you're just, it's like an orchestra. I'm not a musician, but it was keep adding things until it like resembles what the screen would be when we have real samples. And I do think that sort of like building up from simple layers to more complex layers and then concerting these things was definitely the key to going from that poster to this paper.
That was super exciting to me to be able to review such recent work that I knew was going to be so fresh in your mind, having just done the ASMS work about a month ago, but then also publishing so recently. It's super exciting, and I'm just learning more about ion mobility in general through the podcast discussions. And you spoke incredibly highly of the ion mobility mass spec community. For early career researchers listening, how did that supportive environment help you navigate what can be a pretty intimidating trial and error phase of your PhD work?
Oh, honestly, the support in the community and just the general attitude. And these are like the big scientists in ion mobility. Like I've had the pleasure of meeting John McLean, Aaron Baker, Facundo Fernandez, and other people. I'm just Brandon Rutlow, obviously at Michigan. I feel like there's this contrast in how daunting the material is, like when it's presented to you. Like I met McLean and Baker at the first ASMS because I took the short course on ion mobility, and it was just like electrical diagrams and equations, and I'm a little math phobic, which is crazy for an analytical chemist. But I remember being like, oh my god, like what what have I gotten myself into with like committing to this for a PhD? But the contrast between like everything looks so serious, and then they have such a gift in like presenting it like in layman terms or like relating it back to everyday life and like just making it accessible. And I think one of the key things I learned in PhD, at first I was very just intimidated of, oh my god, can I learn these things? This seems so difficult. And I sit down and I read this paper, and it's been 2 weeks of like reading this part of a textbook, and it's, I can't consolidate this. I think advice for early career researchers is like, trust people when they say it takes time. And you're probably facing like the most highly advanced or difficult subjects you've ever learned to date. You'll take more time than you ever have to understand these concepts. But I feel like foundationally having that sort of when the top leaders in the field are like, hey, this is doable. it seems like a lot, but it's doable. That really just like, you're still stressed, but it's like they said it was doable and they know. So yeah, incredibly supportive community, and definitely makes the introduction into such a niche, like no undergrads in first year are like, I would be an ion mobility mass spectrometrist. They just make it really approachable, and I'm very appreciative of that general attitude in the community.
And Laura, one thing that stuck out in your notes when we were discussing your work was I thought it was very cool how you gave credit to not just people who mentored you, but also some of the mentees of yours who helped push the project forward. How did teaching and working with mentees change your perspective on this research?
Oh my gosh, I've had so many great mentees. I think they are all on the paper, except the one I had in my first semester leading up to that bad poster. But they're greatly talented, and they have papers. So thank you. Sorry, but yeah, speaking to the people that are actually on the paper, it was just a pleasure to work with younger scientists or scientists that are coming from different backgrounds. I think what I learned from mentoring, and this is like philosophy passed down from like my undergrad mentors, twofold. First, your mentees are also, scientists. Like they'll have good suggestions, they'll have initiative, and sometimes it's okay, yes, this goes in line with the project, and sometimes this isn't exactly what I was looking for, but if we have time and resources, like I do want people to like test their own like hypothesis and grow that like experimental muscle of I see this, I think this, I do this. And I think that's really great. And I think the other half is also in terms of because I'm mentoring them to help me with something, uh, is like you get really good at streamlining the intentionality of projects, because it's like I personally have a lot of respect for my mentees' time. I feel like undergrad, your time is way more split up than grad school. Grad school is like you just do Droplet, and undergrad, it's like you're doing clubs, you're doing this, you're doing that. So these mentees are incredibly busy. So I think that pushes me as a mentor and just as another scientist being responsible and mindful of their time. What needs to be done, and how can I turn this task into the most efficient version for this student given their time? And that actually develops like another scientific muscle in yourself, which is let's not do things just to keep busy. It's let's do things to get a goal done. um, and it's just really nice to teach that to them, because then honestly I'm very proud of my undergrad mentees. They're really good, and then they just get really good and fast about doing things.
I thought it was really interesting how you highlighted the trade off in screening technologies, where you either get this massive throughput with limited analytical detail, or with traditional LCMS, where there might be deep structural information, but it progresses at a snail's pace. What are constitutional isomers historically such a nightmare for high throughput screening without a liquid chromatography step?
Yeah, I think this, if we philosophize it back to the basics, um, and I had a really nice slide on this in my ASMS presentation. Um, in a lot of like the throughput papers or some of the introductions, it's sort of like, oh, like fast is good, and if you're slow, that's, like we can't do anything with this. And that's my general sentiment. And you might catch on that I'm a pretty dramatic person. But I think if we sort of like, as I said, this back to the basics, um, detectors operate on physical principles, and they are measuring something to do with the chemical identity or like structural properties of the analyte. So, for example, if The beauty of these optical screens is like if you have an analyte that can provide one distinct signal with its chemical formations and the sort of detector setup you have, congratulations, like you're achieving kilohertz throughput. Um, but when you have a lot of these small molecule scaffolds and constitutional isomers in terms of mass spectrometry, you have the same arrangement, sometimes like same arrangement or different arrangement of the functional groups at different points in the scaffold. So in terms of like from a detector's perspective, even a TOF or something, it's like you're measuring the same thing. Like you'd measure the same mass to charge ratio. And if you do like other optic things, it's like you'll just get readouts for the same functional groups. So I think the focus on my project is not so much like constitutional isomers, it's just like this chemical diversity in structures and how we can access these middle level throughput technologies where it's fine. We're not taking 5 minutes with an LC run, but we can do it in 1 second with ion mobility. And okay, we're not at the kilohertz scale, but we are leveraging the state of the art of technologies that are able to differentiate uh, this, obviously by separation, not detection. But we are able to push the analytes we have into higher throughput screening.
And what really just blew me away about this project was your Droplet Cyclic Ion Mobility-Mass Spec platform ended up analyzing samples basically 128 times faster than the standard 3-minute LCMS runtime. When you first successfully ran a 96 well plate in roughly 10 minutes and saw that the data actually matched the accuracy of traditional LCMS, what went through your mind?
Honestly, um, as I had said before, the sort of like the orchestra aspect of my project, I was not surprised. It was this really gratifying sense of I knew it. I knew it because of the design, I knew it because of the way things had been previously validated, as I said, because the sort of like tiers to the orchestra are like, can we make a droplet with this? Can we separate it with ion mobility? Can we do a cal curve? What happens when we add a matrix to the cal curve? What happens if we cross reference every concentration of each isomer in the cal curve? And then you get to the screen. And I think each layer adds confidence of this method works and it keeps working for what we're designing it to. And the more like obstacles to imitate real life interference we add, the method is holding up robustly. The quantification is holding up very consistently. Honestly, I was just proud. It was like, this is my baby and it did the thing. And I was very hopeful. And of course, you always have the, oh, what if there's like a something I overlooked? But at that point, not to say I never overlooked anything, but I looked at enough things so that it did work when we tried that 96 sample screen. And that was a great feeling. That was very gratifying.
Yeah, it's just super cool to hear about, and I know that must have been an amazing moment for you and the rest of the team. In your manuscript, you note that a 5-round directed evolution campaign testing 5,000 variants would take 179 days via LCMS, but only 14 hours on your platform, which is pretty unbelievable. From a synthetic biology perspective, how does compressing months of screening into less than a day fundamentally change the kinds of scientific questions the lab can ask?
Yeah, no, that is a really good question. Again, I'm synthetic biology adjacent, but obviously, in principle, when you're designing these, one of the most like celebrated quotes in screening from Francis Arnold is, "You get what you screen for," and screening really is at the heart of this like biocatalyst development. So I think there's two things I want to say for the answer. The first one is that you can explore more sequence space, because like when you're evolving an enzyme, this is like you're casting a very small net into, I don't have the number at the top of my head, but it's a ridiculous exponent. Like the sequence space that you could have with an enzyme, it's ridiculous. So you're with your screen and your mutants, you're like casting this net, and this seems to be a direction we head down in. So it's let's follow these mutants, and you're navigating this really complex space with what you have. So I think there's obviously a scale advantage here if you're doing it 100 times faster, and you can see how that translates in terms of like weeks to a day. You can in theory analyze more mutants, cover more space, and that's one direct answer. But I think something else really cool that's going on in the field right now with machine learning in particular is that previously you would just take the sequence of your hit enzyme and that would be like all you care about, and then the rest is trash. But now with machine learning and these like other screens, you have negative controls. My collaborator has published a really good paper on this recently. You can start supplementing the directionality of your campaign with more context of, okay, I know the phenotype and genotype of everything that worked and didn't work. I'll use that information to have a more elaborate model to help me navigate the sequence space. And bringing this back to how this plate-based droplet screen could help. Again, you get to test more things, but you're still within a droplet workflow preserving through well plates like the phenotype to genotype relation, which in a lot of droplet works is lost when you're doing everything on chip. Although my lab has some really cool things going on there, but I won't speak to that yet.
Feel free to come back on the podcast maybe next year to update us on how this work is progressing, because it is super interesting. In your results, you showed that increasing the number of cyclic passes dramatically scales up your resolution power, but there is a trade-off there, that the cost is the signal loss, basically. Can you walk us through how you optimize the method to settle on the 3-pass approach? And do you have any advice for scientists trying to find that sweet spot between baseline resolution and signal survival?
Yeah. Oh my God, that is a great question. That is a great question. Okay, so there's the how and the why, and then advice on the trade-off. So I'll get to the how first. So I basically took high concentrations of my analyte, like 10 micromolar, for example, and I had a mix of both isomers, and I just started infusing them into the instrument, turned it into IM mode. I had a previously made method that I developed for another analyte, and I just started tuning that one. And it's okay, how can we, like, you start doing one pass and it's like they're separated, so we start tuning the wave height and velocity. It's okay, it's looking narrower is good. And now we start just increasing the separation time, and that'll be reflected in passes. And at 3 passes with that high concentration solution, I had total baseline resolution. And I do keep mentioning the concentration because there are these space charge effects that sort of broaden the peaks the more molecules you have because of charge repulsion. So that is something I did run into with my higher quantification experiments. I did have that baseline merge a little bit. So yeah, I think this all sort of just speaks to in terms of developing a method with that sort of trade-off, you have to know what concentrations you're going to be working with, how that translates into the optics density, how that affects how many passes you need. And it's this like continuous like check. It's like this loop where it's like, okay, I have something, I'm going to cross test it against this other condition, and I'm going to come back and tune it, and I'm going to see if it works again. And every experiment in this paper was like that. Because the more information you had about the functional system, the more it was like, okay, let's go back and like tweak or optimize something that was like earlier in the layers. And then the second part, advice. Yeah, I think when you're considering something that's a trade off, you just have to go back to your question of what do I want? What am I designing for? Is it better to have like a higher quantification assay that we're not resolving things, but maybe in the data analysis, we can just set like a narrower filter where we crop the merge baselines? Is that something we can do? Or do we really need to maximize the count? Because part of this is just like, as you make things faster, you will make them worse. That is something you just have to accept. But then you have the liberty to choose, what am I making worse? And the core principle behind that is, what can I tolerate to be worse? Again, this all goes back to like that loop. It's sort of, okay, if I do this, my RSD goes up, but I'm going faster, but I don't want my RSD that high, so let me make this other part slower. And again, it's like an ecosystem almost. And it all comes back to the foundational, like I need this to work, whatever needing to work means to me for this project.
That's a great answer. And I know that droplet microfluidics can somewhat famously suffer from crosstalk between droplets, especially with nonpolar synthetic products. You implemented a strategy to handle this, and I'd love to hear about that process and what the final procedure ended up being.
So I think a distinction about my project is that, or about droplet mass spec in general. So typically my lab has done really complex droplet front end workflows like microfluidic devices that can merge and manipulate droplets, and you can grow cells from a single cell into a colony in a droplet and then screen that directly by mass spec. You can do really cool things with droplets on chip. But again, and that's like a everything you do, the more complicated it is, the more problems you'll run into. So my project came up in contrast to what my lab has always done, which is, let's take the simplest droplet infusion system, which is from a well plate into Teflon tubing separated by perfluorodeclin, which is the fluorinated oil, and then we directly infuse that to the mass spec. And it's okay, that sounds easy. And it's, yeah, but the mass spec part was like really obnoxiously complex. So it's like this crossover. The direction we're heading into is taking the super complex handling and coupling it to the super complex mass spec to just make this biocatalysis screening beast project, if I can call it that. So, in terms of how crosstalk affected my project, this is so frustrating. This is so frustrating. I have a personal vendetta against the oil in terms of the electrospray for my project, because my analytes really don't crosstalk while they're in the Teflon tubing. They have some polar functionalities. They're not really going to partition into the fluorinated oil by any means, but uh, they are in about 5 feet of Teflon tubing. And then at the end, they have to go through this 2-inch fused silica capillary that I treated with Rain-X. And there is a little bit of crosstalk there. But the worst part is that when I was infusing these droplets, and I have the camera on the nano ESI source, so it's really fun. You can see the aqueous phase containing your analyte ionize, and that's awesome. And then when the oil comes through, it's not ionizing because we're working below the onset potential. David, I every time a droplet went through, the next little bit of oil would snag the end of it, and when the next droplet came through, it would merge, and I'd have this like little blip of carryover. And I tried like blowing away the oil droplet with air, didn't work. So just frustrating, but there's definitely ways to engineer around that. But my orchestra had too many parts at that point. So we just stuck with a sacrificial wash droplet. But that was very frustrating because I knew it wasn't tubing mediated, it wasn't partitioning, it was just like that one little blip. And yeah, I can't sleep at night because of this.
Maybe it would be good to switch gears more to the data processing side of the project. I know to make sense of the high speed, let's say, data stream, you had to develop a custom data analysis platform to reformat the continuous ion mobility mass spec trace back into well plate format.
Yeah.
How much of a hurdle was the data processing side of the project, and how did you approach writing that software?
Yeah. Oh my goodness. This honestly, I think, is my best, like my favorite story about mentoring. So I'm broadly just a problem solver. And at first, because when you export this data, all you have is an intensity trace over time. So it's low numbers and then high numbers and then low numbers again. And you do have some slight variations in how many scans are like in the intervals between droplets, or how many scans are like in one continuous droplet. So there's no quick and easy way to just do this in Excel. So previously, when I was working with droplets that were all the same, I could just like threshold and do a count function. Or when I was working with calibration curves that were just like 24 samples, I would just sit there for an hour and be like, I'll delete this and label this and average it here, and just very low throughput. So once we were at that tier of validation, that's okay, the next step is to scale up volume. I told my advisor, like, the data processing, like, this is not going to work. You do not want me just manually blocking off things in Excel. So I asked him, oh, can I like put out like a proposal on the undergrad research program at Michigan? And he's, I have to pay for this? And I'm like, no. I think that they pay the student. And he's, oh, yeah, great. So I write up a little proposal. I'm like, this is what the project's on. This is what I'd need to happen. And students could basically go on the website, read the proposals. And I have this student, his name's Aiden. He reaches out to me like, oh, Professor Penabad. And I'm like, no. But he sends out like a really good email. And I offer him an interview. And honestly, this is a story of just like great vibes. Like, he shows up to the interview and he's, oh, I haven't done like software engineering ever, I'm just transferring out of mechanical engineering. And I tell him, okay, I've taken some intro to software, like intro to Python and stuff like that. Like I can talk about like the data structures, I just can't like write functions. But what I could offer you in terms of mentoring is explaining things to you like modularly, because I had a full concept, like I knew exactly what I wanted the software interface to look like. I just couldn't build it. I told him, like, put you in contact with chemists that do software things, and I can explain to you, like, in English and in drawings, and like with some limited terminology, oh, like, this is what I'd like you to do. But you're the guy, you're the software guy. And very confident, very capable. Aiden was just like, okay, yeah. And he had like other interviews lined up with other labs, but he went with the most chaotic, challenging possible option. And honestly, within a semester, we fully got uh, the software up and running. And again, this goes back to like the feedback loop. I started making my assays in a way that the software could pair the peaks better. And then we added some marker columns so that the software could reset at the end of each row. And yeah, it ended up working really well. So you just take the traces, plug them in, tell the software how many columns and replicates you have and whatnot. And then it just spits out like this is the peak ID, the duration, this is the well it came from, just like all the information you'd like. And then in the last iteration, Aiden did make it have a like an auto populate heat map, which was just cherry on top. But yeah, that was a really fun experience.
That's awesome. It sounds like he also joined the most fun lab. So,
For sure, for sure.
and in your manuscript, you note that while the analysis is fast, there's still manual steps like filling a tube and connecting it to the mass spec, and that there's areas of potential improvement to save time. Robotically automating the system, what is the next major engineering leap look like for Droplet MS?
Yeah, I think back to, as I always say, like the philosophical principle of Droplet mass spec, it's like you want to insert droplets into the mass spec as fast as you can meet the following conditions, like having these like discrete baseline, temporally baseline resolved plugs of sample that generate enough information. Sometimes one scan isn't enough. Sometimes you need six scans for droplet. Sometimes some matrices are like they'll increase your RSD, so you have to have bigger droplets or slow things down. Like I always like reverse engineering the system from the mass spec trace because the mass spec trace is the information you want. So I think the big hurdle is just keeping things robust and keeping infusion continuous. So my colleague who already graduated, Bridget Murray, published this really cool paper on using the Venturi effect with adjuvant sheath sources, where basically the gases in the source are like creating this Venturi effect where the tubing is just experiencing vacuum. So you can dip the end of the tubing into a well and you'll just make droplets. So Bridget had worked that up to 96 well plate. Since the next step in this progression of projects that we both participated in is go up to thousands of samples. That's been what I've been working on. And I've done as many as 2,000 samples with just Venturi. Uh, so, yeah, I think going continuous and keeping robust is the next big step. Um, so, yeah, that's I'm just like, oh no, I have to do so much. But yeah, that's what we're doing now.
Very cool. And looking back over your entire PhD journey from your initial poster through this really highly optimized screening platform that you've worked to develop, what's the biggest piece of advice you'd give to a first year graduate student who's really just stepping into the world of mass spec?
I think I'd give a few ground rules and then some mass spec specific advice. So I think in terms of ground rules, people say this and you hear this a lot like when you're going to PhD programs. Oh, you'll learn to think or you'll be better. But I think that at the point where you're at when you start a PhD, education has always looked the same. You learn things and then you take a test and then you like apply them, and that's like the knowledge brain muscle you've been working on your whole life. And then I remember starting my rotation being like, oh my God, my mentor, he can just solve something, or this thing broke and he took it apart. And I was like, have you ever done this? And he's no. And I'm like, what? And I was just like, people just design experiments like on the fly, like for these questions no one has answered it. And I just had this crippling fear of like, can I even do this? Because like I can't do this right now. So I think the first set of things I tell a student going into any PhD is sort of you will evolve. Like the way you acquire and use knowledge will greatly evolve. Like you'll migrate from like knowing things to having this like hypothetical background, and then you get this really like theoretical specific theoretical background in your field, and you start like interrelating things like a multi-dimensional textbook in your head where it's like I'm pulling from orgo, I'm pulling from biochem, I'm pulling from pchem, I'm doing instrumental things. Like you don't learn it the one way as you typically would. So I think the way you hold knowledge evolves, your capacity to understand things evolves, and the way you conduct experiments evolves greatly. And then with mass spec specifically, it's a really daunting, at least for me, it was a really daunting field to get into because it's, oh my God, you have all these like physical principles, like separations itself is like very thermodynamically intense. And then mass spec is very like electrical engineering in the front, and electrospray is still mysterious. It's like this, oh my God, like how do you eat an elephant one bite at a time? And I think that the way you take that bite is like these little steps you make a cycle of. Like you understand something enough to do an experiment, and then you have your experiment, and now you know, oh, like something behaved this unpredicted way. Like, let me go to the theory. Okay, that's why that happened. And you go back and refine your experiment, and you'll find some other detail, and you just start developing this intuition for, oh, if I design this I might run into this. And it becomes like this like beautiful cycle of you're just operating on like knowledge through intuition at one point. And I feel like that's one of the most gratifying parts of being like late stage PhDs, knowing you came from this position of, oh my God, what's going on? I don't think I can do this. I don't understand anything. Just I'm confident in what I know. I'm respectful of what I don't know. And I hold nuance for the in between, but I can do things is just, it makes the 5 years worth it. So yeah, just stay curious and be open to learning and learn that you can learn. So yeah.
All right, this has been so insightful. I think the project was super interesting, and you have so much to talk about in terms of this approach that you utilized with ion mobility and how much faster the process is. And every advancement, I suppose, leads to new challenges, which you highlighted both for the data processing and the software side, but also the future automation to speed up what's now the slower parts of the process. So super interesting all the way around, and I greatly appreciate you coming on and sharing your work with the audience.
Yeah, thank you so much, David. This is really fun, and thank you for guiding the conversation. I know we got to chat a little bit more before the recording, but I'm really appreciative of the opportunity and of your time.
Of course. Thanks so much.